Welcome to our webinar. My name is Andrew Fell. I'm a radio engineer here at TTP, and I'd also like to introduce my colleague Vidhya, who will be talking about some things during this presentation that we've got here for you now. So today's topic is talking about what TTP are doing within the uncrewed aerial vehicle sector. This is the UAV sector, or drones as they're commonly known, and some of the challenges that are being investigated to operate these drones more autonomously rather than having to have them in sight all the time. Hence the title of our talk is Enabling BVLOS, or Beyond Visual Line of Sight. So a lot of the activities that we've been involved in here, we'll go through some of these and give you a background on some of the things we've been doing. Just a quick intro into TTP. We're a development company. We've been around for over 30 years now. There's about 300 of us in terms of scientists and engineer types, working in all sorts of market sectors, from telecoms and healthcare and consumer, all sorts of industrials. We're based on our own science park here near Cambridge in the UK, and we're basically a product development company and develop products for all sorts of clients, from big international companies through to small startup companies. With respect to engineering and the topic that we're talking about here, we develop products in the communications sector and do product development, which encompasses the whole of the product development cycle, right the way from an initial concept, looking at the business use cases, looking at the return on the investments, and how we develop a product to suit that particular scenario and suit that particular business case. So touching now on the topic that we're interested in as part of this. So beyond visual line of sight is the term that's really given when a UAV, an uncrewed aerial vehicle, needs to be able to perform a mission from one position to another. It might be a delivery mission, it might be an air taxi, so people sitting within an autonomous vehicle to go from one place to another. There are lots of different aspects that need to be considered to be able to do this. You can't just fly from one place to another without considering what's going on around you. So 4 elements here are the main things that we have to worry about. Command and control being one of them. This is to make sure that we've got continuous communications from the aircraft to some kind of central position, so that traffic management services and air traffic control know where the thing is, know where the aircraft is, and also the person operating that aircraft has got complete control over what's going on with it. Remote ID is a system which basically makes sure that everyone can see what that aircraft is and the type of aircraft that is flying around in that area. Electronic conspicuity is very similar. It's a little bit like having a radar service and making sure that everyone can see where, in terms of aircraft within an airspace, everyone can see where everyone else is. So it tries to avoid mid-air collisions and things like that. And on top of that, we have the system that's required called detect and avoid, which is the last attempt at making sure that we detect traffic which may not be operating with electronic conspicuity, and thereby having an algorithm to be able to avoid them. We've written the blog on this topic. It's that the link is down in the bottom there, so go ahead and have a read of that if you like. In terms of the command and control section, we've leveraged here on a long-term relationship that we've had within Inmarsat, and we've developed what's called their BGAN radio module, which is basically the core engine of their L-band service using their geostationary satellite. So it's relatively low data rates in the 100 to 200 kilobits per second data rate, but it's great for allowing a reliable service. It's well known for its reliability because the satellites are always in the same space, in the same position within the sky, so you can always get connectivity to it. So it's great for this kind of service. And what we've done, having developed this core BGAN radio module within Inmarsat over the last few years, this has now evolved into a new terminal, which is smaller and lighter weight than has ever been done before, and it allows terminals now to be mounted inside smaller aircraft than UAV type aircraft. So we're talking about weights within the region of 300 grams, including the antenna. We're talking about a device that can do satellite communications and cellular communications. So there's hybrid connectivity going on there to boost the reliability of the communications from the aircraft to some central control point. It's aimed at low cost. So really the idea is to be able to provide a service proposition for aircraft operators to be able to, so it meets their business case. Data rates, as I mentioned before, up to a couple of 100 kilobits per second, which is ample for command and control kind of applications. Some people as well, also some of our partners within this development are now also providing video services over these kind of data rates. So it's possible to be able to use this for video, standard definition video, and command and control on top of that. And the aim for this is also to provide relatively low power. So in terms of power consumed by the aircraft, it's fairly minimal. It's not really expected to make much difference to the power consumption overall. I mean, it depends on the size of the aircraft, but the aim here is to make it as low power as practicable and make it nice and small to fit within small, lightweight airframes. This is the module itself. It's one of our development modules. And you can see on the right hand side here the kind of services that Inmarsat are looking to release. So as I said before, command and control, telemetry, which is all about vehicle health monitoring. You might be looking at battery status, for example, temperatures on board, any kind of information that you might need to know, like pitch and roll of the aircraft and that kind of thing. There's also a possibility of using voice services as well, so using part of that bandwidth for voice over IP. That can be combined as well with video, and basically the ability to provide some onboard edge computing as well. We're providing the ability to plug in an edge compute module, so you can do quite a lot of processing power within this module itself, which allows you to basically compress information that you might want to send over that 100 to 200 kilobits per second link. For example, video compression and telemetry, gathering telemetry information and providing routing between the satellite link or the cellular link. We can do all of those kind of things with the edge compute module. Here's an example of a development kit that we've done. This is a larger version and basically the first of the evolution of the BGAN radio module. So at the moment, as we've got the smaller UAV terminal in development, we are providing an evaluation kit, which we call the blueprint kits, and this allows developers to basically try out BGAN, try out the system for themselves, put data in, power it up, plug in an antenna, and actually see what it's like to operate with a service like this. So you can see the kind of latency effects you can get. You can see the kind of bandwidths that you can get in terms of bit rates, and you can start to develop your application around the system, which can then be targeted towards what you actually deploy on board your aircraft. So this is available now, and if you're interested in getting a hold of one of these, speak to our partners with Inmarsat and speak to ourselves, and we can organise this. In terms of the roadmap, we've got the new devices now in development. They're in the lab. We're doing debugging and characterisation at the moment. So by the end of this year, 2022, we expect to have some flight trial prototypes ready, and then during 2023 we're going to be doing the full qualification of the devices in order for them to be able to become commercially available, and then start with the manufacturing of the devices. So that's one of the aspects that we need to be able to maintain the communications between the aircraft and its operator. One of the other topics that we're going to talk about is detect and avoid, and I'm going to hand over to my colleague Vidhya to talk about what we've been doing in this activity space for this market space.
Thank you, Andy. So Andy talked about sort of the 4 pillars of UAV safety, and if you've been in the UAV sector for a while, you probably have come across detect and avoid quite a lot before. So it's basically, if everything else fails, it's your last mile tactical deconfliction, being able to detect another airspace user and being able to react and avoid them in sufficient time. So why is this challenging, and how important is it at the moment? So there's a lot of activity in this area going on worldwide. I've just thrown in some evidence of some sort of activity that you've probably heard about. So there's a lot of activity in the US, for example. ASTM, International Standardization Body, has released a lot of documentation around aircraft collision avoidance systems. Depending on which altitude you're operating in, if you're below 400 feet, you have what's called SXU that applies to you. And if you're above, depending on if you're a rotorcraft or a fixed wing, you have slightly different rules that apply to you. So there's a lot of specifications being rolled out in this domain. Similarly, in the UK, in 2021, CAA announced a sandbox where it was sort of an invitation to the industry to sort of show the art of the possible in this domain. So this sort of activity basically highlights that this is quite key, and it's quite key from a regulator's perspective to be able to do scalable beyond visual line of sight. And the certification of such a detect and avoid challenge, a detect and avoid solution, is quite key too. So thinking about why exactly is this challenging, because presumably this is already solved in the NAS, right? You are right, but then in the NAS you have many more users who are cooperative, who are what's called electronically conspicuous. And of course, they have a much more bigger size, weight, and power and cost budget to play with. So it's a combination of the fact that you have many more airspace users who aren't necessarily cooperative, and the sensitivity to size, weight, and power that makes this quite a challenging problem. And so you're starting to have to think about this trade-off space of power, the range that you need to detect, weight, cost, the angular resolution that you need to meet, against things like software complexity that you can have on board your UAV, the number of targets that you need to be able to detect simultaneously, and of course, the reaction time that you need. So that in turn determines the range. So depending on where you are and the type of aircraft, the bounding boxes within this trade space might be different. So this is a sort of problem that we started to think about and started looking at what's possible, really. So if what you see currently a lot in the market is what you see there on the right, which is more ground-based solutions. And these tend to work well, for example, if you have well-defined corridors. But moving forward, where you want sort of much more scalable BVLOS doing long-range operation, you probably want to move more to the left, which is onboard. And as you go on board, and if you're talking about a UAV that's very lightweight, you're probably thinking about onboard passive methods, so things like electro-optical and acoustic approaches. So we started to have a play with several different sensor systems to see what's possible. And I'm going to show you some examples of the sort of things that we had a play with. So thinking about vision-based systems, this is an example of where we have Andy's friend who does a lot of flying on his hang glider. And this is a video taken from a very simple GoPro on board his hang glider. And what we tried here is a very simple algorithm where it uses no training data and just takes a frame-by-frame difference and then uses that frame difference to detect motion and hence detect an object. And it's doing fairly well given the simplicity of the algorithm, as you can see. It's actually picking up objects from against the mountains, which is quite impressive. Obviously, it is making errors due to the simplicity, but given it's using a slightly non-traditional approach of not using any training data, it's a good start. We also had a play with sort of more traditional approaches where you have a training data. In this case, it was a data set of helicopters, and actually we intentionally trained it with a slightly wrong data set in the sense that the data set it trained on had a camera looking up rather than looking straight ahead, which is why you can see it's making some mistakes of sort of false detections on the ground. But it's quite representative of what will happen in reality, which is you can't possibly have full data coverage in your data set. And most likely your final solution would probably be a combination of various different approaches like this. But we started with this to basically get a sense of if you had a cheap sensor, right, what can you realistically detect? What realistic performance can you get? we looked at other sensor systems as well, things like acoustic and radar, and we believe a final solution would probably bring the best of many worlds. So just as an example, you could think of an architecture where you had a vision system, which is sort of your first line of defense, and an acoustic system, that's your second line of defense. And the good thing about something like that is that the incremental swap-C that an acoustic system would bring is almost free. So the green table you see there gives you a flavor of sort of the costs and size that an additional acoustic system would need. But the benefits could be quite a lot because, as you can imagine, an acoustic system's range would be much better. But obviously, it can't detect things like a hang glider, for instance. So this is an area that we are actively exploring. But what are we trying to do differently from what's already out there? I think the key thing is that we've set ourselves quite a challenging swap-C goal, recognizing that this is needed in the industry going forward. So just these are sort of numbers that we've come up with based on several conversations we've had with stakeholders in the market. And at the same time, we're ensuring that whatever approach that we select, it has to be there has to be a route to certification. So if, for example, if it's a completely passive method, we have to be aware that it wouldn't be possible to get all possible training data sets from flight hours. So there has to be a route, for example, generate synthetic data that we can then use to demonstrate overall safety of the DAA system to a regulator. In parallel, we've been having a play with some solutions where we can synthesize data. So, for example, this is a capture from Microsoft AirSim, where we took a scenario and introduced an intruder and ran one of our algorithms on it. So, yeah, just as an example of the sort of tools that we have been considering for synthetic data generation. So yeah, I hope that sort of gave you a flavor of what we've been up to in this area. There's a lot of development ongoing. We're working on sort of solidifying our architectures and talking to different stakeholders to assess if we have the right goals. So are we aiming for the right goalposts in terms of range and performance and swap-C? So if you have a specific DAA use case, please come and talk to us. We're very keen to hear from you on what you think is required. If you are interested in sort of partnering with us, for example, in trials, again, we're very keen to hear from you. Given the nature of our business, we're also looking for a partner who can sort of fund and help us bring this to the market. And if this is you, again, please come and talk to us, reach out. But of course, if you just find this generally interesting and want to know more, we're very happy to have an open conversation around this. Thank you so much for listening, and I hope we'll hear from you soon. Thank you. Goodbye.